Well, I like that book.
Yeah, that's a good book.
Hey, all right. Well, hey, welcome back. Let's go ahead and get started. As you know, we've been working here with magnetism, have done our first chapter, and are on our way to our second chapter on magnetism. And let me just kind of highlight where we are and where we're going. This first chapter, chapter 29, was one where we were looking at essentially looking at the forces on moving charged particles. And you might recall we finished that lecture on eventually getting to the grand finale, which was a bunch of moving charged particles, which we'll call current in a wire. That resulted in a torque, and we left with the torque from a motor. I want to pick up there. I think I did 2 examples for you, and I want to do a few more examples in this first hour. And then in the second hour, jump into the next chapter, but only do the first 2 sections. And so that's my goal here into chapter 30, the first two sections. And that's where we'll leave it for the test. Okay, and so you might want to make a note of that. We're not going to have enough time to cover all of 30 for the exam. And the exam is 1 week from today. And so on Tuesday, we'll talk a little bit more about 30. And when I say we, I guess I mean you and Dawn, as you might recall. I'm not going to be here on Thursday. I'm going to be down to San Diego, as I think did I tell you guys that? Yeah, okay. You guys are looking at me like I'm crazy. So I'm taking my son on a little tour down there to 4 colleges. So we're going to go see UCSD and CSU and 2 other schools down there. So going to take a little road trip. Anyways, Don's going to be with you and going through there. And as I think I mentioned, it really has nothing to do with the Chargers game being down there on Thursday night. But we probably should get down there before all the traffic and make sure that, we have nothing to do in the evening that night, and anyways, but I'll be back and then see you on Tuesday. But what I'm going to have Don work with you is and I'll say it again, only the first 2 sections. And you'll see that next chapter is not a long chapter, but it's got 2 main points on how to calculate the magnetic field. There's a first way and a second way, so more on that in a minute. So we're going to cover the first way. That'll be on the exam. The second way is very important, and we will cover it, just not before the exam. So it'll be on the next exam. All right, just to make sure that's clear. And then also, when we were leaving class on Thursday, I got a couple questions at the end of class about brushless motors, and a couple after class, and I really didn't like the answer I gave you because I kind of missed the point of the question you were asking. Yours in particular about the brushless motor. So let me recap on that for a minute here, because here's what I should have said. I got involved in the small gap motor, which is, here's a picture of a small gap motor, and it does use the brushless approach, but that's kind of a subset of the bigger question you were asking: what is brushless motor? So I thought, I answered that poorly, but this is a neat motor and a company that's local here, or semi-local. It's down in Ventura here, and I can even recall 1 or 2 graduates from here who have worked down here. But this is probably a better picture of a brushless motor. And so I thought I'd hook this up again and just kind of address that. You might remember this old Flintstone motor here. And so this is where we left off. This is where it was spinning around. This is our commutator, if you will. This is our brushings, if you will. I didn't bring back out that model I had, but the brushless motor is probably better described as the reciprocal of this, or the reverse of this. And what you do is you put the coils here and you put the permanent magnet here, and the permanent magnet is moving, and so you don't actually pass the electricity in through here, and that's what this is showing here. So here are your electromagnets, and so as you make these magnets, which again will probably be better understood as we do next chapter, where we do coils and the magnetic field created from a coil, but you could then take the rotating part and pull it in, and then of course change the rate at which you change the current in there. So the good thing is we don't have the brushings, and the loss of efficiency, I think, was really what your question was, is why the brushless motors were so efficient. The downside of it, though, is now we need a more complicated computer-controlled circuitry to get the timing right of when to turn on and off the coils in here. And so there's more of a real picture I grabbed. I like this little, I don't know if animation animation is right, but little picture here of showing that, okay, here you have a permanent magnet, and then you can pass current through there. Once the magnet gets in that alignment, you can change it to the B, and that's going to rotate it, and then you can change the current to a C and then a D, and it's like a stepper motor. Or you could move it step by step, and anyway, so like I said, didn't like my answer, and that's like, okay, I'm gonna start off there. And then the second question, actually, and here's the good animation of the thin gap motor. And then what they do is they have both an inside and outside housing, so these two are linked together, and the whole thing moves. And the stationary part here, the stator, is where the coils is, and you don't really even see that. And that's kind of the neat thing about that design right there, is that this whole wheel goes around, and the propulsion part is actually tucked underneath it. And so many different designs as motors, as I think you mentioned. And then the second question was really, well, what could you do to make it lighter? And somebody was pointing out here, well, we could just get rid of these permanent magnets themselves. I mean, the permanent magnets are nice, but they tend to be pretty heavy. So could you use current, if I can stack this without breaking them, could you use the current itself to not only go through the armature, but also through these coils here to make the magnets? And yes, and again, getting a little bit ahead of this chapter, if I turn it around, you can maybe see the wiring here, that if I take this wire and I place it here, what's going to happen is the current can come in and do one of two things. And it might be kind of hard to see here in this model, but when it comes into here, it can go to this coil. And that's the next chapter. We're going to see that coil is going to make a strong field, as well as go through our armature. And so this motor is supposed to be very similar to this motor, lighter in its construction, because instead of having the metal pieces as a permanent magnet, I will use the current itself to do two goals. One is to go into the coils to make this then a magnet, and then the second is to go through the armature here. And yeah, there it goes. And so ours doesn't has a little trouble with it this morning here, but there again would be my electric motor. And then finally, third, I said, you know what, I think I mentioned this in class. I said it'd be nice just to toss around a real electric motor, and you can see something a little bit better than we were discussing here in class. This Flintstone motor that we built, if you recall, we said when it was in this position, it would have the most the least torque, zero torque, and in this position it would have the most torque because of the cross product here, and the torque would change. And so one answer for that is, you'll see here in this design that as it rotates a small amount, just put another coil that is closer to, let's see, maximum torque here. So if I put maximum torque here, then when it rotates a little bit, then shut off the current to this set of coils and put it in a coil that is, again, in a plane that is horizontal. And so that's what you'll see in this design. If I pass it around, you will see that you have a plane of coils, and then if you rotate it a little bit, you have another plane, and another plane, and another plane, and then the commutator is much more complicated. It touches from here to here, but you can see it only makes a small rotation. 1, 2, 3, 4, 5, 6 times 4, 24, 1/24 of a rotation, and then it makes contact with the next one, and then the next one, and then the next one. So always keeping the plane near its highest torque. Now this does use a permanent magnet one, so I'll put it together this way so that you'll be forced to pull it apart when you get it, and you can actually then feel the permanent magnets as they are affecting the coils, and then the commutator is here, but the brushings aren't part of this. And I don't know if you want to pull it around, take it apart, and play with it. Yeah.
So these ones without the permanent magnets, are they more or less
Oh. I'm going to say more efficient. I guess it kind of boils down to what do you mean by efficiency?
Power is used
from the plug?
Supply compared to.
Yeah, then again, my disclaimer is I'm not 100% sure, but given the fact we are not feeding current into the magnets here, and here we are, this would tell me that this is going to need a lot of current. Although, you can make some pretty strong magnets with a small amount of current here. But once these magnets are permanently made, we don't have to run any electricity on them. But then again, we have to make them. And then we have to, if this is a mobile device, then this is something that's heavy and we got to move it. If it's a hand drill, is that efficient?
So if the ones with the permanent magnet were more efficient, that would mean that the magnets were doing work somehow? The permanent magnet?
No, because I would say that, how can I say this? If these were identical, and the current that went through the commutator here was the same, then you would get a certain amount of heating and force here. But what I don't have is I don't have additional current on this one. If this one was plugged in, this one over here would put additional current needed to make these a magnet. So these would be warming. So I'm putting more energy into this machine. You might say I'm getting the same out. So I'm not saying that these do any and then I'm turning it into heat. So that would hurt my efficiency. It's not that the magnets are doing more work, it's that my power supply is doing more energy into it.
So more is lost to heat.
Yeah, and then so more is lost to heat here because these little coils are going to get warm from the resistance of all those wires. All right, well, with all that said, you might recall then we had done 2 examples, 1 and 3. So let me jump over to number 10. There's a couple of neat things I want you to see in these examples. One of them, I think 2 of them are illustrated in this problem if I'm not mistaken here. But number 10 says the following. It says, an accelerating voltage of 2500 volts is then applied to an electron gun, producing a beam of electrons originally traveling horizontally north in a vacuum towards the center of the screen that is 35 centimeters away. Well, there's a lot of words here that you may or may not have caught on, but if you might recall, we spent a lot of time talking about the CRT. That is what this is describing, this cathode ray tube. These are electrons. They say they are going north. They say they've been accelerated by a certain voltage. Here's what they mean by this, is let's just say that we have, and I'll just start with a power supply, and we run it through a very, very thin wire. And you will see this exceptionally well when we do a lab on the oscilloscope because, now actually you'll see it well tomorrow. Let me rephrase that because we're going to have a little electron gun in tomorrow's lab. I think you'll really like tomorrow or Thursday's lab, depending on what lab section you're in. Because this is one of the first steps we do. We hook up a power supply, we hook it to a thin tungsten wire there, and we just get it really, really hot. It's essentially like a light bulb, but you don't get it quite as hot. In fact, you'll see you're going to crank up the dial in the lab until it gives off a little bit of light, but not really kind of a white light. You'll see it kind of orange first, and when it gets beyond orange, then it gets kind of a whitish color, just and as it gets there. But the point is this, that when you get to this high temperature, what's going to happen is you are making the atoms hit so hard that some of the electrons actually bounce off. And so that's step 1 of our cathode ray tube or our electron gun here, okay, is we just get them hot. And we call this boiling the electrons. And so they don't take this description, in here. I think they do a little bit of a job here in the reading. But since you are going to need it for the lab, I thought this would make an excellent time to explain this electron gun here. So first I boil the electrons. Then what? Well, then in addition to having those electrons boil off, I hook it to another set, maybe a huge set of batteries, or in our case we'll just have a laboratory supply. But this is what they're talking about in terms of the accelerating voltage. They're saying take a very large voltage, in this case 2500 volts, and set it adjacent to that. Why? Well, what's going to happen to these electrons? After they boil off of here, what happens? Yeah, they're going to get pulled over towards this metal plate, right? And of course it's at a very high voltage, so that should pull them over with a lot of strength, a lot of force, a lot of acceleration, if you will. Now I put a little hole in here, and maybe I should have aligned it a little bit better with the electrons boiling off here. Because what will happen is these electrons will come racing towards the plate, and most of them will hit the plate. But there's a few of them that happen to be boiling off at just the right angle, right at the right position there, that they actually make it through a very small opening. And that's going to be our electron beam. Because these electrons then have gained their speed from this accelerating voltage, and that's what they're talking about, the accelerating voltage there, okay? So this smaller voltage, which will be around 5 volts when we do it in lab, maybe closer to 4, will first free up the electrons. Once they're free, then your higher voltage will accelerate them, and we won't do anything close to 2500 in the lab. We'll, unfortunately, or we'll have to at least get a reasonable amount of voltage. And so you're looking at 70, 80, up to 100 volts is what we'll set our machine at, which is why when we're in lab, I'll say, be careful with this. And you'll even see on the voltmeter a little, danger sign flash up when we get above 30. And that's kind of our warning to us. Hey, just, now we're dealing with voltages that are, a little too much and a little too dangerous. That's why the machine gives us that display at 30. It's why we always kind of use these most of the time, because they're limited to 20, and that's why I always say, yeah, you're okay in the lab. We're not doing anything except this one that's going to be too much voltage, but we're not going to do the 2500 volts. Anyways, like I said, this was my introduction here to the lab a little bit, and saying this is our electron gun, if you will. And so this is how we make this beam of electrons. So I'll read it again. The accelerating voltage of 2500 volts is applied to an electron gun, producing a beam of electrons originally traveling horizontally north in the vacuum towards the center of a screen. So then what happens here is it comes racing forward, and if nothing else takes place, it would hit this screen and give off a little bit of light when it hits. So as we are moving forward, we are getting closer and closer to having our lab on our oscilloscope. So I thought I'd grab an oscilloscope, a simpler one than the one we had out here before. But you might remember me talking about a little bit about the oscilloscope. And remember, the vertical axis records what? Voltage. Horizontal axis records time. And I think you can even see that if I do something like this and set the clock at a low speed. You can kind of see what's happening, and without getting into too much detail, more detail when we get to the oscilloscope. But what's simply happening is this beam is coming straight through, and the electronics on board are deflecting that beam. And they're first deflecting the beam to one side of the screen, and it just sweeps across to the other. Starts again, sweeps across to the other. Sweeps again, and so you can see the beam sweeping across there. In fact, a lot of times we just cranked up the speed so much that it just kind of looked like a solid line across there. And that's kind of misleading, because I do want you to see that it is a beam moving across there. Well, again, more on that when we get to the oscilloscope, but I just want to change the setting to this, because this is just the beam coming straight out. And that's what they're saying here. So I will adjust the beam until it is hitting the center of the screen. And it's why I brought out the video camera here, so that I can kind of show you something I want you to see. There is the beam right at the center for those of you in the room who may not be able to see the screen where it is now. Because here's the question. This one says that the beam is traveling north. Okay. Which way is the Earth's magnetic field? Is it north? Ah, good. So if I were to draw a picture of the Earth, as we did last time, we said buried inside of the Earth, you could think of that as being a bar magnet. Okay. And we said that if this is the geographical North Pole here, the magnet that you hold in your hand, so here's my compass, and if I place it here, one end of this compass will point towards the north. So if I kind of draw the equator of the Earth here, and I guess I don't want to get into this, but to just be a little more accurate, I guess I should also point out that the little magnet inside the Earth is not exactly parallel to the rotating axis. It's off by about 11 degrees there. Okay, but that aside, I do want you to remember then that the magnet in the Earth has a pole, and a south magnetic pole is in the geographical North Pole. That's why this little end points to the north. You might also remember what the magnetic field looks like from a bar magnet. And I'll just draw half of it. But my point is, if we come up here to Santa Barbara, what direction is the field? Well, let's see. We draw it from north to south. So I'd put an arrowhead that way. And so what direction is it again? It's not just to the north, is it? It's also angled down into the Earth. And so some of you, we got in a discussion about this in the lab, but if I were to tilt this, you can see it a little bit better. That the Earth's magnetic field doesn't just point towards the north, but it dips down into the Earth. And then you can also see that different latitudes would point at different angles. And so it's nice to have your normal horizontal compass, but also a dipping compass, because your dipping compass will give you information about your latitude, as well as holding it flat will give you information about your compass rose, your north, south, east, and west here. And for some of you, gotten a little discussion about homing pigeons, and this is how they seem to navigate around the world. And Caribbean lobsters seem to navigate by walking the magnetic field lines as they migrate from their shallow waters to their deep waters during hurricane season. And I know our lobsters don't migrate, so we don't usually think of lobsters as migrating, but some lobsters do. And those are good examples of really well done science that they seem to pick up on their magnetic field. And I don't think they have conclusive proofs about sea turtles swimming thousands of miles in the ocean yet, but I think that's most of the speculation, that there's some kind of magnetic effect.
So you could use this as like a crude GPS?
Oh yeah, exactly, yeah.
What kind of error would it have?
It depends where you are on the Earth. Yeah. Very much depends on where you're at. You can see, you could get a rough approximation by taking the dipping angle, subtract 11 degrees, and that should be your latitude for a rough. Depending on what side of the world you're on, though. See, because you would either add 11 on this side, you would subtract 11 on this side, and anything in between. So when I say in between, maybe I should look at a globe, because the 11 degrees off is right there. There it says magnetic north. So your compass points towards a magnetic north. And unfortunately, in our case, our compass can be significantly off because of the strong magnetic effects we get from our our mountains, but longitudinal directed mountains, because they were formed north-south, and then with the plate tectonics they have migrated around. So their magnetic was cooled in a north-south direction, and now they've cooled, and so it's like somebody's taken a giant bar magnet and twisted it this way. And so when you hold a compass in Santa Barbara, you know, it can be off 15 to 20 degrees. I'm not sure the exact number from away from north. So if you really want to go north, you don't really want to follow the direction of your magnetic compass. But for most of the parts of the country here, that doesn't happen, especially in the mid part of the country, because they point straight this way, which is straight north. Alaska, you really need to be careful. It's going to be pointing a lot this way and not that way. And so the difference between the direction your compass is pointing and true north can vary significantly depending on where you are on the globe. But like I said, for most of the United States, it's not too far off, because it just happens to be right in the center of the United States. So if you go a little west, a little east. But here on the West Coast, we have the plate tectonics that have switched all of our mountain directions, which foul things up. Oh, anyways, I didn't want to spend too much time on there, but I did want you to see where the author is going with this problem, because the author is trying to say this. Let's go back to the problem here. He says that this beam is traveling north. Now, if this beam is traveling north, that means in this picture, here is the direction of north. I guess here is the direction south. Here is the direction up. And here is the direction down. But if you only think about the Earth as having a parallel or horizontal field, how much force is on these little charges? Well, since the real field looks like this, but if you're only thinking about a horizontal one, wouldn't you say there'd be no force on them? But there is a force on them, because you would have a vertical component. And so as I look at these electrons going that way, which we'll call north, so maybe I should point this way if that helps, but if I got an electron going north, and I've got a component of the field going down, what do I do when I go V cross B? Put my fingers in the direction of V, right? Cross it towards B. And so wouldn't there be a force on the negative particle this way? And so I claim that this particle, when drawn this way, would be V cross B, since it's an electron times a negative charge, and this electron should be curving away from the center of the screen due to the Earth's magnetic field. Now I can adjust everything so it still hits the center of the screen, but that's why I brought out this video camera here. Watch what happens when I rotate it. Right now, if I take and adjust the position of that little dot, and let me turn down the intensity so it looks like a little smaller dot. How about right there? Would it be fair to say it's hitting the center of the screen? Now, what if I were to rotate this? Which is why I brought the video camera out, because you can't see it when it's back here. Is it at the center of the screen anymore? No, right? It's been deflected. And so this moving charge is deflected because of the Earth's magnetic field. And so like I said, I thought it would be a good example that could give me a chance to talk a little bit more about the Earth's magnetic field, as well as the electron gun, and then to the main point of the chapter, shouldn't there be a cross product? Shouldn't there be a force on this moving charge? And that's what this one is saying. Watch, if you keep reading here, it says, The electron is originally traveling horizontally north in a vacuum towards the center of the screen 35 centimeters away. So this is 35 centimeters. A, what is the magnitude and the direction of the deflection on the screen caused by, and this first question is, say, gravity. All right, so we'll just go all the way back to Physics 121 and our mechanics here. What they do want you to see is the effect of gravity is really, really small. But let's do it. All right, so A is, here I have this screen, okay? It's going to go horizontally. Isn't it going to get pulled down? I mean, if you start off horizontally, how much will it get deflected? Well, is it distance equal to 1/2 AT squared? Or maybe the way we're used to writing it, let me write it as the y direction. Y, and if I write it as initial position times initial velocity in the y direction times time plus 1/2 acceleration in the y direction times squared. If I apply this to this case and say, okay, it's going to come out of my electron gun going horizontally. Let's call that position 0. It has 0 initial velocity. It then has an acceleration of 9.8 downward, and so maybe I should put 9.8 meters per second squared, and then it should have a time squared. So this boils down to how much time does it spend? Well, that's where the horizontal equation comes into play. And so again, if you remember your horizontal calculations here, if we call the starting point horizontal, it has an initial speed in the x direction and no acceleration in the x direction. And so really it is how much time does it spend here. And we can get that from the speed. Where can we get the speed? Isn't this the accelerating voltage here? So applying conservation of energy, I can say the initial electrical energy is then converted into kinetic energy. And so that energy, the potential energy, came from this 2500 volts. So what I have is the charge of an electron multiplied by the 2500 volts goes into the speed of this electron. So the charge of an electron is 1.602 times 10 to the minus 19 coulombs. The voltage, they are telling me, is 2500 volts. The mass of the electron is the 9.11 times 10 to the negative 31. And there's my favorite number again for fall. We see it again here. It's been a while since we used it, but now that we're getting real close to Halloween, it's a perfect day, all right, to mention it there. All right, and then there's my speed squared. So I got a little bit of calculator work to do, but once I do that, I can figure out then what is the speed. So 1.602 times 10 to the negative 19 times the 2500 gives me the energy, about 4 times 10 to the minus 16. Multiply by 2, divide by 9.11 times 10 to the negative 31, take the square root of all of that, and we're looking at a speed. How many zeros is that? Divided by 7. All right, so this is about 2.97 times 10 to the 7th meters per second. Small speed or big speed? Yeah, really, really big speed, which is what the whole point here is to see. This is how you get the speed. You get the speed from the accelerating electrons. You go back a bunch of chapters to find out what the speed is. Once you get the speed, you're going to realize that this is such a short amount of time, this thing barely has a chance to fall. So how much it moves because of gravity really can be ignored. That's what I want you to see in it. Yeah.
So after the electrons pass through the gap,
Yeah.
doesn't that potential difference pull them back towards it?
Fair enough. So there's a couple things we can do here, and it's probably a little better to do this way. That this will be the ground. This will be the ground. And then really what I'm operating as a negative 2500 volts here. And so the electric field is all between here. There is no electric field in here. This whole case is now grounded and at zero. So instead of thinking of it at zero up to the 2500, it's really the other way around. It's the whole case is grounded and this is below, and so you're bringing them up. So there's no field on this side. Put another way, it's if this is 2500, what if I made the whole case 2500? I made the screen 2500. There is no change in potential. It's all at 2500. And so there is no electric field in here. Of course, I don't want the case to be at 2500. So I would like the case and everything else to be at zero, and then all the internal stuff to be at then a lower voltage. Okay, so heading back over to here, here's my speed of these electrons, and now I can come over here and say, okay, this is the 35 meters. It is going to be traveling at 2.97 times 10 to the 7th meters per second. It is going to give me a very short amount of time, 0.35 divided by that last answer. I changed the last answer. Okay, let's try it again. Divided by 2.97 times 10 to the 7th, resulting in just a small fraction of a second here, 1.17 times 10 to the minus 8 seconds. Knowing that number, I can then come over here and go 1/2 times 9.8 times that small amount of time squared, coming up with 6.8 times 10 to the minus 16th meters. Okay, so, right, it's 1,000,000 times smaller than an atom. An atom's about 10 to the minus 10th. This is 1,000,000 times smaller than an atom. So fair enough to say that it doesn't really fall that much because of gravity. The time is so short, the speed is so much. Don't be surprised then if all the problems we do talk about what is the magnetic effect, what is the electric effect, and forget the gravitational effect. And you'll see that again and again in the examples that I do and in the examples you will do on the homework here. And you saw it, I think, here, although you saw me twist it and you saw the magnetic effect, but I didn't change gravity, so I don't know if we can say that I showed you the minor effect of gravity, but at least I showed you that the electrical effect is definitely, magnetic effect is definitely noticeable. And then that's the next part of the question, and really the main part of the question is B, what is the magnitude and the direction of deflection on the screen caused by the vertical component of the Earth's magnetic field? Take it to be 20 microteslas down. All right, so the vertical component here is 20 microteslas, is what they're saying. And obviously it would vary from where you are on Earth to Earth, but at about our latitude, that's a good working number for what is the vertical component of the Earth's magnetic field. So now if we redo this problem and call this B, we can look at the force acting down on it. I suppose we have to either do a little more math to make it exactly accurate or approximate it and make things a little bit simpler. And I'm leaning that way if it's okay with you, because let's look at the direction here for a moment here. If this object is going this way, and the magnetic field is this way, what's the direction of the force? Right, okay, so I take my right hand, there's V going this way, right? Cross B would be that way. Now that's not the force yet, because that's just V cross B, so then when I multiply by a negative, it's out of the board. So in this configuration, if this is north, then if I stood behind them and watched them go north, they would deflect to my right. So if I point north watch them go that way, they would deflect to my right, which you would say, I guess, is east. Okay, so they're going to deflect to the east, and they're going to go out of the board here. And so the question is, how far do they come out? Now, maybe I should ask, what path do they take? Is this like gravity, where they make a parabola? Or is this a part of a circle? Yeah, it really is part of a circle. So I suppose to do this accurately, we really need to be part of a circle. Although, I think they've set it up here that this is so far and this is so little that a parabola or a circle is going to be roughly the same, although they're going to do a problem in a minute where they won't be roughly the same, and we're going to have to do exactly a circle. So tempted to just approximate it, like we just match up what we did and then change that when we get to one that requires more detail. Yeah.
You said that the gravity was very small.
Right.
As it passed through there, the further it went, the closer to the direction of the magnetic field it would become, and therefore it would have less acceleration as it went further.
I'm not sure I caught that. What?
So on the left, it's experiencing 100% of the magnetic field acceleration, right? And then on the right, the gravity is going to cause it to tilt downward. So it's going to be closer to the direction of the magnetic field, and therefore less force from the magnetic field.
Oh yeah, okay, but remember, it moved down less than a millionth of an atom.
Right, I know it's small, but it's still not the same. It's not uniform.
Oh, well, okay, so if this angle was 35, then I guess you're really saying is, what's the angle now when it has tilted down 10 to the minus 16, when it traveled 0.35 meters this way, right?
You're saying it's small, but I'm just saying it's not zero.
Okay, and I'm saying it is so small that you're not going to be able to measure it. And therefore, it's not going to be calculated. Yeah, fair enough. However, if you take that one step further, I guess we could also argue that the amount of bending this way is really always the vertical component. As it starts to head off in another direction, then that's going to start curving it up or down. So even if you do include this angle, that doesn't affect this way. It starts now deflecting it up and down, because that's the component of that field. In other words, as it is heading towards the east here, then you can start including this field, right? That's what you're saying, the horizontal field, which would be an up-down motion.
I was saying the longer it goes on, the closer to the direction of the magnetic field it becomes.
Okay, fair enough.
Change in angle is
but I'm saying it's small, not going to count. All right. So again, we can argue, is that important or not? And I'm saying no, not that angle, not important. Okay. Okay. Now, what I guess I'm getting at here is I might just use the same time frame. That time. Oh shoot! I erased it. What was the time? Okay. So if you go ahead and let me keep that same time and just say, you know what, it's going to roughly keep its same horizontal speed as it comes shooting through here. That is assuming it doesn't move too far over that way, right? Because again, what I do want to make sure you remember here is that as this object is going, and if it is curved by a magnetic field, as it is curved by the magnetic field, its speed does not change. The magnetic field does no work on it. But its incredibly large speed this direction, if it doesn't change too much, so if you're talking about a small distance, and I think you saw that, right? The part of the reason I wanted you to see this is I did want you to see it did not deflect very much on this screen, and yet it is traveling about, well, this is even less than the 35 centimeters. So 35 is probably a little bit longer here. So if you will allow me then to make another approximation here, And then on the next problem, I won't do an approximation because we can't. But on this one, do an approximation by saying, you know what? The time it takes to go across is pretty much the same, because even though it loses a little bit of its horizontal speed, it's just that, a little bit of its horizontal speed. And so it's still going to take that same amount of time to go in that direction. And therefore, if I go ahead and I calculate then the force to the east, that is this QV cross B that we just discussed, right? This is, and maybe we'll go through it again here, right? If my beam is going to the north and there is a vertical V cross B is west, multiplied by the negative electron is going to get it to go to the east. So there is a force being applied to the east, and it would be equal to this. It would be the Q, the V, and it would be the vertical component of the Earth's field. You can see that when you write it as QVB sine of theta, where theta is whatever number is there. Yeah.
I don't understand why does the speed not change? It's got this horizontal speed, and then you have this eastward force on it. Wouldn't it just get an eastward component?
Oh, if the force always remained east, yes. But it doesn't. Here's what happens. Again, let's call this direction east. So if I'm that little electron and I'm going north, and at first I have a little push to the east, that kind of deflects me just a little bit because my force is perpendicular to my direction, right? No work. I don't go any faster.
Why not?
Work.
Okay, but you had this, there was no force in the I guess, north direction to slow you down. That component.
Right, but remember, work has a dot product in it.
Okay.
So to do any work, you have to have a force that is in the direction you are moving. So a ball on the end of a string has a lot of force on it because of the tension. But it doesn't make the ball go any faster. It doesn't make it do any work. All that force does is change the direction of it. And so likewise too, this electron goes this way and it's pushed to the east. Now, at that point, it's heading a little towards the east, but also the force changes. The force isn't really towards the east. The force is, according to this, the force is always perpendicular to the velocity. So you're always pushing it sideways. Okay. Now, again, we're approximating this and saying, look, let's just say the force is always to the east. Hence, in that case, you would say the force or the speed to the north doesn't really change. Like I said, it's a rough approximation, but given these fast speeds, I can get away with it on this one, I think. And so there is the force. Now, to do what we did before, y equals initial position plus initial velocity in the y direction times time plus 1/2 acceleration times squared. If we do exactly what we did before, we can call the y direction, and maybe I should call it z direction this time because I'm really going out of the board, okay? But sideways to the beam, this would be 0 plus 0, and I would have 1/2. The acceleration would be the q, the v, and the b over the, that's force, over the mass, and then time squared. And so this is how far it's going to deflect due to the magnetic force. So there's the 1/2. The Q is the 1.602 times 10 to the minus 19th. The velocity was 297. Anybody remember that from A? Okay. 7. The magnetic field in the vertical component of it, and I should put vertical here, is 20 microteslas. The mass is the 9.11 times 10 to the negative 31, and then the time is the 1.17 times 10 to the negative 8th squared. And so that's roughly how far it should deflect. And again, roughly, because I am, making those approximations. But you'll see that this number is small enough that it'll justify these approximations. And then much bigger than the gravitational force, but still not very big. So 1/2 times 1.602 times 10 to the negative 19 times 2.97 times 10 to the 7th times 20 micro divided by 9.11 times 10 to the negative 31 times 1.17 times 10 to the negative 8 squared, coming up with 0.007 meters, 7 millimeters. So there should be a noticeable deflection on this one. 7 millimeters is certainly very noticeable on the screen. Mine was less than 7 millimeters, but it looked like it was 4 to 5, about what 4 millimeters was what mine looked like there. So I got about half of that deflection. Yeah.
So if the time difference was significant, then would you just set up 2 equations with 2 unknowns?
Yeah. Now, right. If you mean if it deflected enough.
So the time was significantly longer.
Yeah. Yeah, then there's no way I would be able to justify that it kept its same horizontal speed. And I would reanalyze this one with a circular motion. And I'll do that in just a second. Yeah. But this one doesn't need it, but it was a good one, at least I thought it was a good one, to give you a lot of pieces that an electron gun you're going to see in the lab tomorrow, and how this thing works, and then the deflection of the magnetic field. So that's why I picked it as a good example. It was both a good calculational example and one that also allowed us to do a little bit of calculation. Okay. So this is force. Force divided by mass is acceleration, right? So that's Newton's second law. And maybe it'd be a good time to just throw that out there. Again, remember, a lot of mechanics here, and so we keep going back to Newton's second law, F equals ma, projectile motion, accelerations.
So which part of this is an approximation?
The part that's an approximation is this time. Because that assumes it keeps the same speed in the x direction. That's the part we derived in part A. And that's not what's going to happen. This thing is going to be moving along and has a very large speed in the x direction, but as it bent, if it bent a lot, then its speed in the x direction would get smaller and smaller and smaller, and the time to the screen will get longer and longer and longer. Okay? But this was such a small amount of bending that I approximated it. Yeah?
35 degrees, that was given?
Oh, no, that was, I picked 35 because we're at 35 latitude. But notice, and maybe I should emphasize that, notice this angle is not needed. Why? Because right here, when we do the cross product, it says the angle between the V and the B. And so that's that. And so these two together, the Earth's field and the angle, is the vertical component of the Earth's field. And that's all they've given me. So that is that piece of the puzzle. Okay, so I don't need the angle. I just need to know that the vertical component, which is the total field and the angle combined together. Now the one I was referring to is in a TV monitor, and here you want to deflect the electrons quite a bit. This is a pretty big monitor. I'm trying to remember the number. I'm thinking it was 23. Yeah, look at 23 here, if you will, for a second. It says here, in a picture tube, in a TV, uses a magnetic deflecting coils rather than an electron deflecting plate. And so I should add to this, we are talking about the deflection due to a magnetic field. Couldn't they also be deflected with an electric field? And in fact, if I put a positive and negative plate inside of that, wouldn't that deflect the beam up or down? And that's actually what these oscilloscopes have. When we take these apart in lab, you're going to see that if I look at this oscilloscope and I grab this button here, I can make the beam go up or down. Up, down. And I could even make the beam go left, right. Left, right. Okay? And in that case, it's being deflected by an electric field. So we can have either ones. And so in a TV monitor, they tend to deflect them with the magnetic field. In that oscilloscope, they tend to deflect them with the electric field, so I can control it a little bit better. But again, this is an identical problem like that. It says this: a picture tube in a TV uses magnetic deflections rather than electric deflecting plates. Suppose an electron beam is accelerated through 50,000 volts and then into a region of a uniform magnetic field that is 1 centimeter wide. All right, so let me clean up the board here a little bit and say, okay, my picture is going to change a little bit. In this electron gun, in this cathode ray tube, in this old-fashioned TV type, they're saying this is 50,000 volts. So there's my 50,000 volts. Now, again, taking from that last chapter, doesn't this tell me the speed of these electrons coming out? That's the key to it, that they will tell me the speed. And then what they're saying here is it enters an area where there is a magnetic field. Now, the magnetic field is probably created something like you saw at the beginning of this lecture with current that is going through these coils. And so you have the TV electronics that then sends the current to these coils, and that's going to make a magnetic field. Let me illustrate the field in green, since that's what your author does in your textbook. And so there will be the magnetic field. I'm putting little X's, meaning the magnetic field goes into the board here. All right, so it says here, suppose that the electronic beam is accelerated through 50,000 volts into the field that is 1 centimeters wide. The screen is then located 10 centimeters from the center of the coils. So if you can imagine a giant coil here, what they're saying is from the center here on out, this is where the electron beam is going to hit. This is 10 centimeters. So making your TV, you kind of want to make that distance as short as possible, right? And that's the whole reason why this type of design doesn't exist really much more in these worlds, because you have to give yourself a little bit of space. And right there, they're looking at, you know, at least 10 centimeters right there, which is pretty short in itself, but it's still, you know, 4 inches there. So we've got the 10 centimeters. But then it says, let's see, read it here. The screen is located 10 centimeters from the center of the coils and is 50 centimeters wide. So this TV tube is 50 centimeters from top to bottom. And if you want this electron then to deflect and hit the bottom of the screen and or the top of the screen, you're going to have to make sure it deflects vertically quite a bit of distance, 25 centimeters down or 25 up. In fact, in the configuration I have now, V is this way, B is into the board, V cross B is up. Since these are negative electrons, the force would be down, and so this thing would enter and curve and head something like that, right? So that's the design goal. This is what the electrical engineer is trying to figure out what to do. We want these electrons to be able to deflect all the way down and hit the lower part of the screen. And then when we change the magnetic field to the other direction, we want them to be able to deflect all the way up. And so there's our deflection. And I think you'll see in this one, obviously, this distance is definitely significant compared to this distance. In fact, it's 2.5 times. So I need to think about that. Of course, what has changed is I have a magnetic field only in a small region of space, and I'm ignoring the Earth's magnetic field there. I probably shield it in some way so that hopefully it's not too much affected by the Earth, yeah.
Didn't you say that was an electric field?
No, this one's magnetic.
Okay.
Yeah, sorry. They did say, at the beginning here, they say this. They pitch your tube and a TV uses magnetic deflecting coils, not electric deflecting plates. Okay, so this is, again, magnetic. Okay. Suppose that the potential difference it is 5,000. Suppose that it is the magnetic field is 1 centimeter wide. Suppose that the screen is 10 centimeters from the center of the coils, and suppose that the screen is 50 centimeters wide. When the field is turned off, the electron beam hits right in the center of the screen. What field magnitude is necessary to deflect the beam all the way to the bottom or top? Okay? And so obviously I think you can see that as the field gets stronger and stronger, in other words, if the field started off 0, the beam would go straight through. As you increase the field, it would deflect down a little bit. And as you got to the strongest field, it would deflect all the way down. That's the point here. So how strong do you have to make that field? That's really the key here. And in this case, I'll change colors if this helps, but hopefully you'll see, doesn't the motion in this part have to be the arc of a circle? Right? And it deflects so much that we can't just, ignore the change in the horizontal component like we did last time. So I'm going to put something that looks like this and call this radius R. Okay? But here's really the key to this problem. That electron is going to then be part of a circle by an angle theta. And if you draw this back, since here has no magnetic field, that would be a straight line. And if I draw this back and I draw a tangent there, it's going through the center. I'm sure that's why they gave me 10 centimeters to the center part. But I could ask this question, what is this angle? And I think that angle mathematically is going to be pretty easy to find, isn't it? Because isn't then the tangent of this angle, let me call it alpha for a second. Tangent of alpha is 25 centimeters over 10 centimeters. And that's going to give me my first angle. And so what do I get when I take the inverse tangent of 25 over 10? And so that's about 68.2 degrees. 68.2 degrees. 68.2 degrees. Why do I care about that? Well, look closely here. If I draw a four-sided object, what is the sum of all the angles in a four-sided object? Isn't it 360? And if I'm drawing tangent to the circle, those are 90 degrees, 90 and 90. So aren't you really saying this far angle over here and this angle add up to 180? But aren't you also saying these two adjacent angles are supplemental, add to 180? So isn't that angle really that angle? Yay! All right, so a little bit of geometry, and a little bit of mechanics. stuff that we haven't directly done in this class, but stuff that I know you have done and hopefully haven't forgotten, we can get that angle, right? And so there's my angle. Now, why do I care about that angle? Well, again, let's look at one more bit of geometry, or maybe I should say trigonometry, but I claim that can give me the radius then. And then once I know the radius, then I can finally get to the stuff that's in this chapter and get away from the mechanics here. But as I look at this, this is the radius. This is 1 centimeter. Sine of theta is the opposite, 1 centimeter, over the radius, isn't it? Okay. And so this little blue triangle right there is opposite over hypotenuse. Opposite over hypotenuse. So R is 1 centimeter divided by the sine of 68.2 degrees. And there's going to give me my radius. And so 1 divided by sine 68.2 degrees. 1. I probably eventually do want to convert to meters. But in this step, I'm not doing any energy or work or anything else that has got meters in it. It's just a trig ratio. So far I have not converted, obviously, to meters. So I'm just going to leave it there. But yes, I probably want to convert because I'm going to use magnetic field in Tesla, and Tesla has meter in it. So I definitely will convert here real soon here. But and maybe it would just be wise to convert now, and I'm going to have to do it eventually anyway. But I don't have to do it here, is what I'm getting at. But I will eventually have to do it, yeah. All right, now with all that said, this really gets us back to our chapter. Our chapter, we learned that the magnetic force is this, right? That means the magnitude of the force is QVB sine of the angle theta. Right? And so if we now look at the magnetic force on this, what is the angle theta? Now, let me specify. Theta in this equation. Not theta in this equation. I mean, what was theta here? This was this angle that I was looking for. Fair enough? But what do I mean by this theta? The angle between V and B, right? Okay. So here's this electron. And when it first comes in, what's the angle between V and B? Well, V's that way, B's that way. It's 90, right? Now, a little bit later, it's angled down like this. So V's this way. Which way's B? That way. What's the angle? Still 90. All right. So this can be just QVB. But like a lot of these problems, it really illustrates, be careful with your angles. There's a lot of angles that show up. Okay? And this is a good example of something I haven't said for a while, so it's worth saying. If all you do is memorize the equations with the idea that you're going to plug and chug, this is going to kill you. Right? These are the types of problems you won't do okay on. The ones you will. Overall, you'll do okay, and over time, you'll do okay, and transfer to an okay school, and have an okay career, and make an okay salary, and you get the idea, right? All right. But plugging and chugging can get you into a lot of troubles if you're not really reading the physics behind those. And I think this is a good illustration of that this is the angle between V and B, whereas this was yet another angle that I had used in the geometry of setting it up there. Okay, and we saw the same thing with our electric motors last time. So be real careful. Anyways, now I can go to my mechanics, which is that, right? And so if I know it's going in a circle, it's mv squared over r. That's our chapter 6 from Physics 121. Then the v's cancel off, and I get r equals mv over qb. Right? And of course, the other side of this puzzle is, what is V? Yeah, and that's why we spent time talking about an electron gun. V you got from this accelerating potential. So the charge of the electron times the accelerating potential is 1/2 mv squared. And so if I bring the 2 to the other side, and I'll use a capital V for voltage, hopefully not to confuse that with the little v for velocity, I then have the square root of 2 times q times the accelerating voltage over the mass. And there are a few things that cancel off. It looks like the magnetic fields I'll leave out here. In the numerator, I will leave the square root of 2v alone, but it's these guys here. Let's see, this is the square root of q over a q, which means I'm left with the square root of q down there. And then this is the square root of m with the m up there, so that's the square root of m. So it looks like I got the b outside of the square root, but the 2, the m, and the v, and the q all inside the square root. And so this then should be the radius. And what am I after? Magnetic field, right? So my final step would be to say magnetic field equals 1 over the radius times the square root of 2mv over q. Fair enough? And in the interest of time, since I've already talked more than I really wanted to, but I want you to see a couple more examples here, is, can I leave that alone and let you punch it in? And that would be the magnetic field. Because another fun one to see is actually number 29. Yeah, question. How'd I get what?
How did I get the magnetic field to stop exactly at that position?
You don't. This is overly simplified. But you'll see we can do some pretty rough approximations as we get into the next chapter. And some pretty good coils. But no, that's where you, kind of cross the world from, pure calculations and what you might call pure science. Oh, we're going to calculate the field in, and then we just start doing some approximations and say, let's build our first generation and see what we get. And then we have to do some engineering. We build it, we modify it, and say, you know what, the field's not quite like that, so let's tweak the coil. And even these stopping the field like that has really been an evolution with time, and that each manufacturer has just constantly taken their magnetic coils and bend them and tweak them a little bit more and say, oh, that works a little better. Don't tell anybody. And so the shape of their coils is very interesting to look at when you take their TVs apart because of that. Now I forgot what number I said. 23? No, 29. Yeah, this is Ignite. That's the little one. But here's a neat application here. Back to the computer here. All right. But look at number 29. 29 has this little picture here, and it says, let's take a rod. A rod of mass 0.25 kilograms and radius 6 centimeters rests on 2 parallel rails that are 12 centimeters apart and have a length of 45 centimeters long. The rod then carries a current of 48 amps in the direction shown and rolls along the rails without slipping. A uniform magnetic field of 0.24 Tesla is directed perpendicular to the rods. If it starts from rest, what is the speed of the rod once it leaves the rails? And did you catch all that? I mean, there's a lot of details in the number, and we'll put it in here, but let's just look at this for a moment. You've got these rails that are probably hooked to a very large power supply over here. Okay. the current flows down this rail, across the rod, and then back along this rail. But the point is there's current here. Now there's a lot of current. They say 48 amps. Okay? Which actually is small compared to some of these rail guns that we're going to be discussing here. But look at what happens. Is there a force on this rod? Right? If the current is going this way, in fact, maybe I'll put the equation on the board, but now that we've done all these forces for these individual charges, one of the other equations we had was the magnetic force was the current L cross B. Actually, maybe I should start a little smaller. It started with a little bit of force is equal to a current times a little bit of distance times the magnetic field. Do you remember that equation? And so that's how we change this equation when we had a lot of charges flowing. We called those a lot of charges the current. And we said, okay, this is that field. Now, if I integrate both sides, and for the special case where the direction of the wire doesn't change, and isn't that what I have? During this rod, isn't the rod always pointing in the same direction towards you? Okay. And isn't the angle always the same between the magnetic field and the current? All right. So in the simplest case, we can just take this equation, factor out the I, factor out the angle, factor out the magnetic field, and we end up with that. And so that's probably the simplest form we can have for the magnetic force. And so I'm looking at the magnetic force just on the rod, okay? I know that there would be forces on the rail, but let's assume that the rails are bolted down, they're locked into place, and if there's forces on them, great, but they don't move. But what can happen to this rod? Yeah, it can move, can it? So what direction would be the force on this rod? Take my right hand, right? The current's going towards you. B is going down. So I cross B is that direction. So it's going to roll along this rail. That's the idea. And in this case, here's what they say. They say that the rail is 45 centimeters long. Watch, I'll read it again here. It says, a rod of mass here's the rod, 0.72 kilograms, radius of 6 centimeters is at one end of the rod. A rod of mass 0.7 kilograms and of radius 6 centimeters rests on two parallel rails that are 12 centimeters apart. So the rod goes back and is resting on another rail. That distance from rail to rail is 12 centimeters. And the length of the rail is 45 centimeters. The rod carries a current of 48 amps. So going through this rod is 48 amps of current in the direction shows. The rod then rolls down the rails without slipping. A uniform magnetic field of 0.24 Tesla, so the magnetic field 0.24 Tesla is directed straight down. Okay? It is directed straight down and perpendicular to the rod. If the rod starts from rest, what is the speed of the rod as it leaves the rail? Okay? And so obviously this is going to move down the rail and leave with some speed. So let's give it a little calculation. Again, hopefully you will see that this is a combination of A, what did we learn this chapter? B, all that wonderful mechanics that we learned previously. So I will start off with this particular chapter. There would be a magnetic force. And as I said earlier, this would be the magnetic force. It's how much current, how long is the rod, what is the angle between the rod or the current and the field, and then multiplied by the field. So I will put this as IL B sine theta. The I is 48 amps, as they say. Okay. What's L? So is L the 45 or the 12? It's the 12, right? The length of the current. So this is my 12. Again, be careful here. It's one of those examples where, look, we have an L here, but we also have an L here. Don't just blindly plug and check. What do these mean? This is saying this is the force on the wire. So this is the length of the wire that's carrying the current. That's what I want to know. What is the force on the rod? And so this is the length of the rod. And so I got it labeled here as an L. And it's just tempting for me to confuse it with the length of the L in that diagram, but that's not what they mean. They mean the D in that diagram. Okay? Magnetic field. I know the magnetic field. This is 0.24 Tesla. And then the angle. What's the angle? 90. Good. 90 degrees. Right? And so as this thing rolls down, no matter where it is, the current is still going out towards you as it moves down. And the magnetic field is down, and so that's still 90 degrees.
So wouldn't you have current flowing through the rail?
Oh yeah, you'd have current flowing through the rail also.
Would that interfere with the motion of the rod?
What do you mean, interfere with it?
I mean, wouldn't the current going through the rail create a magnetic field of its own?
Yes, it would. And actually, that's why this field is even here. When you really build these things, they look more like this picture. That the current coming down this rod makes the field, then the current goes across here. Now this picture is the reverse of the one we have here, but this one is going to push the rod that way because of the field. So yeah, there is an interaction. But again, you're getting a little head of that picture. So they have not said where this field comes from, other than there is a field. But yeah, this one would create the field. Okay, but it would be in the opposite direction. So this must be some kind of external field. So that probably wouldn't be a good design. So we'll modify this design in the next chapter when we actually add that added piece to it. But anyways, this is the part I wanted you to see. So how would I calculate then the work, which is equal then to the change in kinetic energy? There is, back to my physics 121, right? There's the work energy theorem. So I would take all this number, the 48 amps, the length of the rod, which is the 12 meters, the size of the field, which is 0.24 Teslas, and then say, if you apply that much force, and there's my distance, right? I apply that much force on this rod as it goes all the way down, then that's the work. And that's really what I wanted you to see. The other part's mechanics, but it's worth reviewing. So let's do the other side of the equation. What's the other side of the equation? So this is the work. So here's force. Here's distance. And that equals, okay, how do I get kinetic energy? I heard 1/2 mv squared, yeah? And then it rotates. And so I don't want you to miss that. So that's why I'm asking, right? Right? We've got to give our energy to this rod. This rod is both translating and rotating. So please don't forget that last piece. So this would be a 1/2 times 0.72 times v squared. And I think that was the question. Now I've spent all this time, I kind of have lost track of the question. What is it? What is the speed? Right? So there's the mass and there's the speed. There's the 1/2. Oh, I. There's a good one. What's I? It's a cylinder, right? And the moment of inertia of a cylinder is? But if you forgot, you know what chapter to find it?
7 or 8.
It's 10. So in chapter 10, we learned that that was the moment of inertia of a rod. And so it is then rotating, and so its angular speed without slipping is V over R. And then fortunately the R's cancel off. And so it does simplify a little bit. That's 1/2 plus 1/4. So 1/2 and 1/4 makes 3/4 times its mass times its speed squared. And again, maybe to save a little bit of time, I'll say, why don't you just, and at the risk of putting more burden on Don on Thursday, I'm going to do one more. But I got to show you this picture then, because I just love these things. Here's a diagram of a real rail gun. I mean, don't put the energy into rotation. I mean, that's just spending energy on making it rotate instead of making it translate. But if you really want to make this sucker translate, I mean, put a couple thousand amps down this rod, put this across here, and so here is your loop. The magnetic field is actually created by the current that's in this plus and minus here, and this is just going to zip this thing down at, I'll show you a picture here, but I mean, it's so fast that this thing starts to vaporize. It turns into a big plasma as this thing goes so fast. In fact, this actually breaks away. You fire this thing along, and after it leaves the rail, the outer housing, which is used to conduct electricity, falls away. This is your bullet, if you will. This is what you're trying to shoot, that little pointy object there. The picture right before this had the guy holding it. Here it is. That's a nice little projectile. Send that through an incoming missile, and there's nothing left of that missile here. So here's your kinetic energy weapon. And some of these energies and some of these speeds are amazingly fast. Here's a photo of one flying through the air, and it's just turning into a giant plasma. It almost looks like it's got rockets on it already, and it's just ionizing here. And so the amount of speed they can get out of these things is actually more kinetic energy than if the whole thing was loaded with explosives. So you don't even put explosives. It's got more energy just by impact than it does by shooting a regular old-fashioned cannonball type projectile at it here. And so there's a lot of energy here, and so it's often referred to as kinetic energy weapons instead of chemical energy weapons. And they can really get ripping. NASA's constantly experimenting with these. Can you launch something into space this way? Forget all the chemicals and the rocket engines for it. Can we just make a giant rail going through, I guess it would be Central Florida, and zip it on through and launch it up into space? I mean, can you get that 17,000 miles an hour that you need? And I don't know if they've got it that high. They've got some pretty high speeds. And of course, now you've got air resistance too. So even if you get 17,000, you need 17,000 above the atmosphere. So who knows if the future will open the door for, launching satellites this way. Yeah.
Well, Superman the Ride, isn't that made with magnets?
Which one?
Superman.
Oh, yeah. And it's a little bit like this. It's probably more like the motor that I got started, where you have coils, and then you turn on the coil and that pulls it forward. Shut that one off, you turn on the next one and you pull it forward. And yeah. Well, as I said, at the risk of taking a little too much time, but I think maybe we'll have just enough time to do sections 1 and 2 here. Let's look at, oops, I shut everything off. Let's look at number 55, because I haven't really done one with a motor yet, or the torque from a motor. This isn't exactly a motor, but it's a good one that is, again, going to require you to think about what did we learn in this class and add it to what did you learn in your mechanics class here, right? And so let's look at 55 here. It says this. Here's the picture. They say a non-conducting sphere of mass 80 grams and of radius 20 centimeters. Okay? Or just a non-conducting sphere has a mass of 80 grams and a radius of 20 centimeters. A flat, compact coil of wire with 5 turns is wrapped tightly around it, with each turn concentric with the sphere, as shown in the figure. The sphere is placed on an incline that slopes downward to the left, making an angle theta with the horizontal so that the coils are parallel to the incline, not parallel to the ground. A uniform magnetic field of 0.35 Teslas vertically upward exists in the region of the sphere. What current in the coil will enable the sphere so that it will rest at equilibrium on the incline? Show that it does not depend on the angle theta. In other words, we want this to remain at rest. I mean, let's say there was no magnetic effect. You put a ball on a hill, what happens? It rolls down. Which way? All right, down the hill. In this case, it would roll like this, right? If we go back to our mechanics and do our right-hand rule, we would say it has a torque this way, right? It has a torque out of the screen. So what do we need? A torque into the screen, right? We need this to be pushing it up the hill. So one of the formulas we worked out towards the end of the class was this. The torque from a coil is N, number of turns, times the magnetic moment cross the magnetic field, where the magnetic moment is the current in there times the area. And the area also being an area vector, meaning that it has the magnitude of the area of the coil, but also has a direction, and the direction is perpendicular to the plane made by it. So looking at this cross section here, I have this coil here. I have this incline. Of course, it is wrapped around this sphere. Something like that. They show the magnetic field upward that way. The torque has to be mu cross B. Now, mu has to be perpendicular. The direction of it is perpendicular to the surface. So I guess mu could be either this way, there's mu, or there's mu. There's the magnetic moment. Which way do we want the magnetic moment? Well, you can take my right hand, right? Mu cross B. If I put my fingers in the direction that's up, close it towards B, I get my thumb into the board. Whereas the other way around, I get my fingers pointing down, close towards B, I get out of the board. So this magnetic moment would be the wrong direction. That would help push it down the hill. So it would definitely go down the hill for 2 reasons. Gravity is pushing it down the hill, and the magnetic torque is pushing it down the hill. So the correct magnetic moment would be this way. And then hence the current, and we didn't get enough time to really mention this, so I thought I would mention it, but when we said the magnetic moment, we said that the magnetic moment is perpendicular, and it's defined as your fingers are going in the direction of the current. So looking at that, I can answer part of this question, which is going to ask me what direction does the current travel, and so as looking down from above, I would say counterclockwise. Because if it was going clockwise, I would curl my fingers with the current and my finger would be pointing down, or my thumb would be pointing down. And so that tells me the necessary direction of the current. We've got to figure out, and now I have forgotten what are they doing. It says, what current in the coil will enable the sphere to rest at equilibrium on the incline? and then show it does not depend upon the angle. So there is my torque from my magnetic field. So again, if I apply what we've learned in this chapter, I can do the following. I can say N is the number of turns, which in this problem they tell me it's 5. The magnetic moment is the current times the area. So there's current and there's the area, right? If I take a loop that is wrapped around a sphere, it makes a circle, and the area of a circle is pi r squared. Then I would have the magnetic field, and then I would have the angle. And I should probably ask, what angle is this? Okay, I called it theta. And then, oh, they put it in there? Ah. Well, and I guess really that's my question. Is this the same theta? Are they different? You see, this is the incline, right? What does this angle theta here mean? Doesn't that mean the angle between these two vectors? So this is theta, right? Although, if I do a little geometry here, and maybe I'll just extend that angle maybe to this edge. There's B going up. There's mu off to the side. There's theta. So that would be theta, right? So this would be 90 minus theta, and so that would be theta again. All right, so that theta is the same as that theta. All right, so if I wasn't paying enough attention, I got lucky this time. But I bet my teacher knows when people are going to get lucky or not pay attention. So I wonder if it'll be that way on the test. Or will it be sine instead of cosine? Right. So again, pay close attention to, again, what these mean. So yes, in this case, they've set it up so that had you not given this enough thought, you probably would have just called it theta and gotten lucky because it does be the same theta. So it is the same theta as the slope of the incline. So there's the torque. And notice it's not 90 degrees this time, right? All right. And so and there's my torque. But that's up the hill. What's the torque down the hill? Well, again, now let's go back to our mechanics. We should probably do our free body diagram. Here's our free body diagram. Let me just put the sphere right here. Gravity's pulling it straight down. There's mg. Normal force is pushing normal to the surface. And frictional force is keeping it from sliding down the hill. So when you go to calculate the torque due to gravity, and maybe I should have emphasized, this is the torque due to the magnetic effect, okay? Of course, torque depends on what axis you calculate it. So I need to be consistent. When I was over here, wasn't I calculating the torque about the coil? That's the center. All right, so I need to do the same thing over here if I'm going to say torque up the hill equals torque down the hill, right? And so how much torque do you get from the force of gravity? None, right? It goes right through the center. And maybe I should, R cross F of gravity. That's a 0. The other torque, R cross F from the normal. How much torque do I get there? 0 also, because again, it goes right through the center, or you might say the angle there is 0 degrees. But then I get a torque which is R cross the static friction, right? And that does not equal 0. So that's the part that is, if you will, making it rotate. And you can kind of see that. If there was no magnetic effect, if this was just back to physics 121, you would have looked at this and said it rolls down the hill. It rolls this way. It rolls this way because there's a torque. What's making it roll this way? Well, there it is, right there, right? That frictional force is supplying the torque, right? So the nice thing about that is the distance would be the radius of the sphere, the amount of force would be the static friction, and the angle would be so I hear a 90, I hear a theta. Which is it? Now it's the angle between R and F. And the angle between R and F is 90, yes. Okay, so that one is 90 degrees. So don't put a theta there for that one. So again, we have an angle, which has to do with the torque from gravity or friction. We have an angle, which has to do with between the magnetic moment and the magnetic field. And we have an angle that has to do with the slope of the hill. This one's 90. The other two are the same thetas.
Sorry, where would the static friction come from then?
Where does the static friction come from? When you put two objects together, there's a roughness between each one.
Oh, you're saying the ball won't slide down the hill? Is that what you're saying?
Right, so there's a coefficient of static friction times the normal. And so there's an interaction between the roughness of the ball. Right. And and if we didn't have a static friction, and maybe I should do that. So far I've only done torques. But if we do the force here, I can look at the sum of the forces and set that equal to MA. And if I look up and down the hill here, you can kind of see that I have pushing it down the hill is mg sine theta, where this is theta, which is, yes, the same theta as the slope of the hill. Pushing it up the hill, so maybe I should say down the hill, pushing it up the hill is the static friction, and that has to be balanced. So there's our definition of static equilibrium. The sum of the forces have to be 0, and the sum of the torques have to be 0. And so, this thing can't slide up and down, and it can't rotate up and down. And so when I put those two pieces together, I've got the torque, which is Ni pi r squared b sine theta, has to equal to the torque from the friction. And the frictional force has to be enough to balance the gravitational force. So that's mg sine theta. And so notice, as the question asks, show that this would not depend upon the angle of the hill. Kind of makes sense. If the angle increases, this increases, but once you do that, you are increasing the amount of friction to hold it up there because you have a steeper slope. More friction means more torque from gravity, but it also means an equal amount of more torque from the magnetic. And so, as the problem said, show that this thing will be balanced at any angle, just you got to find out what current it is. And so our unknown here is the I. And in the interest of time, may I stop there and say you can put in your numbers and solve for then I. What is the amount of current in order to get this crazy thing to balance? Fair enough? Uh-oh. Some of you are looking at me like you're not ready for the test. And fair enough. You still got a week away, so you got time for this to sink in. But we do need to make sure we cover this one more piece here. And so in the short time that I have left, let me at least introduce. Oh, that is a nice picture of a firing railgun. Wow. Wow, that's the opening picture to your next chapter here. But the chapter begins with an opening picture like this. This is figure 1. And really starts off and says that the goal of chapter 30 is to show you now how to calculate magnetic fields. Let me just emphasize, did you catch everything we've done here in chapter 29? I mean, we did a lot. And granted, it wasn't that much, or it wasn't simple stuff. Although, I'm suspecting that a lot of the stuff that may not seem simple is because we're integrating it with our mechanics from last semester. But really, we only did this in chapter 29. In chapter 29, we said that the force on a moving charge is equal to this. Then if you put a bunch of those moving charges together, then we said, well, there'll be a little force on a current where all those moving charges represented the current. And then if you put that in a loop, the net force on the loop would be 0, but there would be a rotation to the loop. There would be a torque. And so that really kind of summarizes, in case you missed all that, what we did in chapter 29. That's exactly what we did. We looked at a lot of this, and then a bunch of mechanics. Or this, and a bunch of mechanics. And then this, and a bunch of mechanics, right? But if you recall, in none of this chapter 29 did I at once tell you how to get the magnetic field from a calculation. But we did start chapter 29 and said, where does all magnetic fields come from? Yeah, moving charges. And so that's probably the best place to begin with chapter 30 and say, remember that statement that we made at the start of 29, and that is your magnetic fields come from moving charges. That is, they come from currents. And so what I'm really saying here is our source of magnetism comes from our little currents. And so there should be a way to calculate magnetic fields from currents. And there are 2. And that's what this chapter is. There's a 1 and a 2. And as I said, we're just not going to have enough time to do the second method before the test. So what I want to focus on the rest of today, and then some calculations on Thursday, is the first discovery by 2 scientists, Biot, Savart. The 2 of them figured out how to calculate the magnetic field from what I would call point sources. The best thing I can say is this is an analogy to Coulomb's law. Didn't we learn how to find the electric field from a point charge? Didn't we learn that the electric field was equal to this Coulomb's constant times a little chunk of charge divided by the distance squared, and it would be in the radial direction. Do you remember all that from chapter 23? And we learned how to find the electric field from a single point. Why was that so important? How was that useful? Because nothing's really a point, right? But what did we do? Then we used our calculus, right? We summed up what a real object would work. From that, couldn't we find the electric field from a rod? And we did. And a circle. And we did, right? And so if we knew how to do it from a point, then we had the skills, in theory anyways, to do it for any shape, because all we had to do was add up those points. Now, number 2, I will put on the board for completeness as we get started with the chapter. But this is what we're going to have to continue on next week after we do the exam. It was Ampere's law. And Ampere's law, I would say, is analogous to Gauss's law. And if you remember Gauss's law said calculate the electrical flux through some kind of closed surface, and that would equal to the charge enclosed. And we used then the argument of symmetry. We said, hey, to use Gauss's law, we've got to kind of know conceptually something about the field already. And of course, that's why we did Coulomb's law first before we did Gauss's law. And way back when we did magnetism, your author gave you 2 chapters to do this. I guess he figures now you're so sophisticated. And this is so easy for you now that you've been doing it for 8 weeks. Why would you need 2 chapters when we can just put them together? It's, I think, probably best if they were 2 chapters. So I'm going to treat it that way. And that's why I said I'm going to go to this point, which is section 1 and 2 of chapter 30, and stop and say, okay, that's where we'll take the test. Then after the test, we'll pick up and start doing the rest of our magnetism. And that'll be on the next test here. But this is what I want to show you today. This is Biot and Savart's discovery. And so we call this the Biot-Savart law. And it simply says this. This picture gives it away the best, but here's what I want to emphasize and what little time we have left. You need to know what each of the symbols mean. Otherwise, you won't use them correctly, you won't integrate correctly, and of course, you won't get the right answer. So, let me come back over to here. Do you remember what each piece meant here? Or maybe I should have put a DE right there. But probably the most important piece was this. Isn't the charge what creates the electric field? So as I look back at what we did in chapter 23, I would say, if I wanted to know the electric field right here, I would come over to here and say, the field at this point is created from that charge. Fair enough? Now let's extend that to our magnetism. Here's my question. I've got a long wire, and let's not worry about the whole wire for a moment. Let's look at a small chunk of the wire right here. This little chunk of wire should create a magnetic field. Okay? And so your author is saying, look at the point P. The point P is where we'd like to find the magnetic field. So I would write this as a little bit of a magnetic field. A little bit of magnetic field, just like a little bit of electric field, is created by what? Well, I think you can see one of the factors over here is going to be the source, right? Current. Now, you can probably also see why magnetism tends to be a little bit harder calculations than electricity, because for electricity, couldn't you literally have just a single small charge right there and no other charges around? For magnetism, can you have just a small little current with no other current around? No, that current's got to get there and then it's got to leave. So we're always going to have to figure out what is the total magnetic field by saying that chunk plus 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 that chunk. So we're always going to have to do an integral. We can't just have one single point. But that's okay, because we did a lot of those, even though we can introduce it as a single point charge. So that's the analogy, that we have a certain current. All right? Here we got a small amount of charge. We just have to add up all of our charge. In this case, we have a little of current, and that little current is really the main source. Well, probably not a surprise, because we did a lab on this, and we saw it for electricity. When you got further and further from this chunk of charge, didn't the field get weaker and weaker? Wasn't it inversely proportional to the square of the distance? And isn't that how magnetic fields also taper off? Wasn't that the whole point of last week's lab, was to measure the magnetic field and see that the magnetic field got weaker and weaker with distance? So yeah, don't be surprised There's an r squared down there, sure. So the source is the current, and of course how far away you are. It kind of makes sense that if you were kind of close here, you would expect to get a stronger field from this little chunk of current as opposed to being over there. Okay. Just like electric field. If I was a little closer, I'd expect to get a stronger electric field from that little chunk of charge than if I was further away. And then likewise, wasn't there some kind of conversion factor, some kind of constant, depending on what kind of units you have? And we have the same thing. In fact, why don't I skip a step and say, do you remember that even though we first introduced it as Coulomb's constant, didn't eventually we change it into more constants that kind of broke down into the 4 pi for the spherical symmetry and the permittivity of free space, right? We can do the same thing here. We can break this down into a constant that includes how does the magnetic field permeate free space, and then the 4 pi. For better or worse, we write it with the 4 pi downstairs, I mean with the constant upstairs instead of downstairs. And you'll see the helpfulness in that later on. But in either case, we call this then mu naught, and that's then the permittivity, or excuse me, permeability of free space. And be careful there, because one is the permittivity, one is the permeability, right? And I got to admit, I always got to stop and think about, okay, now which one am I talking about? Am I talking about the magnetic field? Or am I talking about the electric field? And its number, fortunately, is a little bit easier to memorize. It is 4 pi times 10 to the minus 7. Whereas if you remember over here, permeability, permittivity of free space was our 8.85 times 10 to the minus 12. So that one I think was a little bit harder. This one is real nice because it's got the 4 pi. Look what's going to happen on my first step of my calculation. 4 pi times 10 to the minus 7, what's going to do with that 4 pi? Yeah, it's going to cancel. And so this whole thing together is just 10 to the minus 7. And so it's one thing nice about the calculation. All right, I'm almost done here, right? Let's see. I've got what creates the field. I've got how it tapers off with distance. I've got the constants. The only last thing I'm missing is the direction. And this is where it does get quite a bit different than electricity. Because what direction is the magnetic field? Well, you can kind of see here that was the dilemma we had when we got started. Remember, the magnetic field was perpendicular to the direction of the electrons that created it, and it was only the perpendicular motion that was relevant. So, if the current is in the screen, and we are looking over at some distance, that magnetic field would then be perpendicular to these two vectors, which means it's out of the board. And so the magnetism, I think, does become a little bit harder, part because to visualize it, you got to picture this in 3 dimensions. How do I get a vector that's out of the board? Cross product, right? And so there's our cross product. What's ds? Well, ds is the direction that these currents are moving. Isn't that the stuff that's making the magnetic field? And so we want to know how much of the motion here is perpendicular to straight over to there. And so that's why we do a cross product. And so the cross product of the vector going to the point in question and the little ds is what gives me the direction of the magnetic field. So watch this right-hand rule. If I take my right hand, if I put my fingers in the direction of S and I close it towards R, don't I get out of the board? And isn't that what that little picture says? What direction is the magnetic field? Out of the board, right? Look at down here. Oh, wait, how's that? All right. So, I will set this up, but it looks like I'm going to run out of time here. But the first very useful calculation is really this. What if we just make the simplest calculation we can? What if you have a wire that is straight? How much magnetic field do you get from this straight wire? Could you do that? Well, let's see if these codes make sense. We got enough moments, I think, just to write this out. But if I took that picture, okay, and I said this, I said, all right, how do I get the total magnetic field? Isn't the total magnetic field the summation of the magnetic field from that chunk plus that chunk plus that chunk plus that chunk plus that chunk, right? And so if I have a wire that I want to know the magnetic field right here, then I guess I would add this first chunk to the next, 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 to the next. And you can see that your author labels this as theta 1 and then theta 2. Actually, in that picture, he hasn't gone quite that far. But here would be the integral. The integral would then look like this. You would have an integral. You would have mu naught over 4 pi. You would have current I. You would have the ds cross the r hat over r squared. And now you have to add up chunk by chunk by chunk by chunk. And so, the first step is probably the easiest step because everywhere along this straight wire, don't I have the same current? Here's where it gets hard though. Let's take this cross product. The cross product would look like this. Now let's talk about this. What is this cross product? How do you take a cross product? It's the magnitude of the first one. Well, what do I mean by the magnitude of the first one? ds. What am I adding? dx. Times the magnitude of the second one. What's the second one? r hat. How long is that? 1. And then times sine of what angle? It's between these two, right? So when I write sine of an angle here, what angle am I talking about? It's this one. Not that one. This one. So maybe I shouldn't write it as theta. Excuse me. Maybe I should write it, excuse me, as 90 minus theta. And then it would be labeled in the same one they have there. Fair enough? And then what's r? Well, r would keep changing too, right? But fortunately, what would you say about the tangent of theta? It'd be what? X over A with a negative? Why the negative? Right, because if this is going to be your origin, these are negative x's. So if you're going to let that be a positive angle, you need to represent that with a negative inside. Well, we're out of time, and that's unfortunate. I'll let Don finish this calculation. But this is not that simple of calculations, but it's the simplest one we can give you. What is the magnetic field from a wire? As simple as that. One straight wire. What are you going to get? Then we'll do some harder ones.